Hello everyone. Today we'll be solving Cambridge IGCSE Chemistry Paper 6 Alternative to Practical May June 2021 Paper 61. Question number 1. Many indicators are colored substances obtained from plants. A student extracted the colored substances from some berries using the method shown. A. The berries were crushed. In B, the crushed berries were heated in water to form a colored solution. In C, the solid was removed from the colored solution. The question says name the items of apparatus A, B, C. So we can see for A, we can see it's a mortar and pestle. So we'll just call it mortar because it's labeling towards the mortar. And B, we can see it's a tripod. So we'll name it tripod. And C is actually a filter funnel. Part B. The student analyzed the colored solution using chromatography. Complete the diagram to show where the spot of the colored solution should be placed on the paper. The level of the solvent in the beaker. Baseline drawn in pencil. We can see the chromatography paper. So we'll have to place a spot where we're going to place that particular solute that we're going to test. And then we'll have to give the solvent. The solvent must be below that spot. So part 2. Explain why pencil is used to draw the baseline on the chromatography paper. Because pencil is made of graphite and graphite is not soluble in the solvent. Part C. The student made 2 chromatograms. After chromatography, 1 chromatogram was dipped in dilute hydrochloric acid and 1 was dipped in aqueous sodium hydroxide. The results are shown. You can see red and blue, and we can see blue and green. Chromatogram dipped in hydrochloric acid, chromatogram dipped in aqueous sodium hydroxide. Determine the number of colored substances in the solution obtained from the berries. So, because in each of these we can see there are 2 spots, so it will be 2 colored substances. So we're just going to say 2. Part 2. The table gives the color of some indicators in acid and alkali. Name of indicator: anthocyanin, color in acid red, color in alkali blue; bromothiamyl blue, color in acid yellow, color in alkali blue; Congo red, color in acid blue, color in alkali red; methyl purple, color in acid purple, and color in alkali green. Use the data in the table and the results to give a possible identity for one indicator in the berries. Okay, so let's try. The indicator that turned red in the hydrochloric acid also turned blue in the sodium hydroxide. So red in acid, all right, so it can be anthocyanin, and it was blue in alkali, so it can be anthocyanin. Question number 2. All students investigated the temperature decrease when sodium hydrogen carbonate reacts with dilute hydrochloric acid. The student did 6 experiments. Experiment number 1. Using a measuring cylinder, 25 cm³ of dilute hydrochloric acid was poured into a conical flask. The initial temperature of the acid was measured using a thermometer. 1 gram of sodium hydrogen carbonate was added to the conical flask at the same time a stop clock was started. The acid and the sodium hydrogen carbonate mixture in the conical flask was stirred continuously using the thermometer. The temperature of the mixture after 1 minute was measured. The conical flask was rinsed with distilled water. Experiment 2. Experiment 1 was repeated using 2 grams of sodium carbonate instead of 1. And then experiment 3, it was 3 grams of sodium hydrogen carbonate. Experiment 4, it was 5 grams of sodium hydrogen carbonate. Experiment 5 was 6 grams of sodium hydrogen carbonate. And experiment 7 was 7 grams of sodium hydrogen carbonate. So use the thermometer diagrams to complete the table and calculate the temperature decrease. Calculate the temperature decreases. All right. So we can see mass of the sodium hydrogen carbonate slash gram. Thermometer initial temperature, we can see we'll have to read from 20 degrees Celsius upwards. So this is 22. So we'll read it as 22. And the thermometer reading temperature after 1 minute, we can see that it has gone below 20 and it is in between 19 and 20. So we will call it 19.5. Alright, so the temperature decrease will be 22 minus 19.5, 2.5. So we'll repeat the process. We can see here it's again 22. Alright, so we can see in every experiment is starting at 22. We can see this experiment starting at 22.5. We can see this experiment starting at 23. And we can see this experiment starting at 23 as well. So 23 we're going to write. Now for the temperature after 1 minute. So we can see this is 17, 15, 16, 17. Alright, so we'll just label it 17. Alright, so 22 minus 17, the change in temperature is 5 degrees Celsius. Then we can see this temperature is between 15 and 16. So we can see it's gonna be it's a temperature between 15 and 14. So the temperature is going to be 14.5. So 22 minus 14.5 is 7.5. We can see over here that it's 14 and then this is 13. Alright, and then that will be 13.5. So 22.5 minus 13.5 is 9 degrees Celsius. Alright, this is 16. And the next one is 16 too. So we can see in both cases it's 9 degrees Celsius. Part B. Plot the result from the experiment 1 to 6 on the grid. Draw two best fit lines through your points. The first straight line should be for the first 3 points and must pass through 0, 0. The second straight line should be for the last 3 points and must be horizontal. Extend your straight lines so that they meet each other. So basically what we will have to do is we'll have to do two best fit lines, and the point where they are going to meet is going to indicate that that mass of sodium hydrogen carbonate is needed for neutralization. So first of all, we'll do the plotting. Part C1. From your graph, determine the temperature decreases and mass of sodium hydrogen carbonate where your straight lines meet. Include appropriate units in your answer. Show clearly on the grid how you work out your answer. So whenever the question says that we'll have to show clearly in the grid how we worked out our answer, it's about it. They mean extrapolation. So we'll have to show the extrapolation. So the temperature decrease is 9 degrees Celsius and the mass of hydrogen carbonate needed is 3.6 gram for that. Now part 2. Explain why the temperature decrease becomes constant for high masses of sodium hydrogen carbonate. So basically for high masses of sodium hydrogen carbonate, the understanding is that all the acids, the reactants are used up. Part D. The investigation was repeated with dilute hydrochloric acid of half the concentration but the same volume. Sketch on the grid the graph you would expect to obtain. Label your line D. So because we are going to use half the quantity, we are going to use half concentration. Half concentration refers to half the quantity of the acid in terms of moles, even though the volume is same. So since we are going to use half the quantity of the acid, we are going to need half the quantity of sodium hydrogen carbonate. So sodium hydrogen carbonate will be 1.8 gram that will be used. So it will be here 1.8 gram, and then it will meet up until this particular point, 1.8 gram. So the line will just go straight from the origin up until 1.8 gram, and then from there it's going to plateau. So as a result, the temperature change will be 4.4. We can see here the temperature change is 4.4. So 4.4. Now part E. Suggest two changes that could be made to the apparatus that would improve the accuracy of the result. For each change, explain why it would improve the accuracy of the result. Because this particular experiment is a experiment where we are finding change in temperature, so we can use a polystyrene cup or a styrofoam cup which can act as an insulator to reduce any heat gain. And for change 2, we can say that because in this investigation we were using the measurements, we were taking the volume using measuring cylinder. Now we know that measuring cylinder is not as accurate for measuring fixed volumes like 25 cm cube. So instead we could use a pipette. Solid E and solution F were analyzed. Tests were done on each substance. Test on solid E. Test 1. About half of solid E was placed in a test tube and heated gently. Steam was given off. Condensation appeared near the mouth of the test tube. So whenever a particular solid is heated and that produces steam, and that steam it condenses back again, and we can understand that that is water, then basically we understand that the particular solid is hydrated. It indicates hydrated salt. The remaining of solid E was dissolved in distilled water to produce a solution E. The solution was divided into 4 equal portions in 3 test tubes and boiling tubes. About 1 cm cube of dilute nitric acid followed by a few drops of aqueous silver nitrate were added to the first portion of solution E. So nitric acid followed by silver nitrate is a test for either chloride, bromide, or iodide, as in general halide present. Then there is the answer that comes, the result that comes is no visible change. So we can say no halide present. Test 3. About 1 cm cube of dilute nitric acid followed by a few drops of aqueous barium nitrate were added to the second portion of solution E. So nitric acid followed by barium nitrate is a test for sulfate. White precipitate is a positive test, so sulfate present. Test 4. Excess aqueous ammonia was added to the third portion of solution E. Alright, so when excess ammonia was added, we can see white precipitate. All right, now ammonia, adding ammonia to a solution, and then if we see white precipitate, it can indicate and then it says excess. We know there are three things that produces white precipitate with ammonia, that is aluminium, zinc, and then calcium. In this case, also, okay, so zinc, aluminium, and magnesium, these are the three ions that produces white precipitate. Now out of these two ions, we know, sorry, my bad, aluminium and zinc, these are the two ions that produces white precipitate. So out of these two, zinc will dissolve in excess ammonia, so aluminium could be that present in that white precipitate. Excess sodium hydroxide was added dropwise and then in excess for the fourth portion of solution E in the boiling tube. White precipitate which dissolves in excess to form a colorless solution. So sodium hydroxide and then white precipitate is a clear indication of aluminium ion, and we already confirmed it, all right, from the previous experiment test 4. Test 6. The product from test 5 was warmed gently and then any gas given off was tested with damp red litmus paper. The damp red litmus paper turned blue. If we have a particular salt, when we heat that particular salt, when we heat that particular salt with sodium hydroxide and we get a particular gas that evolves, that gas turning damp red litmus paper blue, it's always ammonia. Any gas that turns damp red litmus paper blue, technically for IGCSE syllabus, should be ammonia. And a presence of ammonia is an indication that there were ammonium ion present in that particular salt. Now the question A, state the conclusion that can be made from the observation in test 1. So we can say from the test 1, the salt contains water of crystallization, or we can say solid E. Part B, state the conclusion that can be made from the observation in test 2. So test 2, we can say that there is no halide present, not a halide. So the salt that we are talking of does not contain halide ions. Identify the 3 ions in solid E. So we can identify in that there is ammonium present from the last test. Also from the test from sodium hydroxide and ammonia indicates that there is aluminium ion present. And then finally we can also detect that there is sulfate ion present. So aluminium, ammonium, aluminium, and sulfate. Well, the formula is not necessary, but I'm just writing it. Test for solution F. Solution F was aqueous sodium hydroxide. So we already know there is sodium ion present, and we already know there is hydroxide ion present. Complete the expected observation. A flame test was carried out. Presence of sodium ion will give yellow flame due to the sodium ion. The remaining solution F was divided into 2 approximately equal portions in 2 test tubes. The first portion of solution F was a few drops of universal indicator was added. The observation was, well, if we add, because sodium hydroxide is a base, and if we add few drops of universal indicator, base should turn universal indicator blue. Part 2. To the second portion of solution F, approximately 2 cm cube of aqueous copper to sulfate was added. Observation. So to the second portion, now to the second portion, if we add copper to sulfate, now we know that sodium hydroxide will cause the copper 2 ions to basically form a blue precipitate. Copper 2 ions reacts with sodium hydroxide to produce blue precipitate, and it is insoluble in excess. So our answer will be blue precipitate. We can say blue PPT. Last question. Dilute hydrochloric acid reacts with calcium carbonate to make carbon dioxide gas. The apparatus shown in the diagram can be used to follow the progress of the reaction. The carbon dioxide gas leaves the flask, causing the mass shown on the balance to decrease. And we can see there is cotton wool that is stuffed at the top. There is calcium carbonate. There is dilute hydrochloric acid. There is a balance. Plan an investigation using the apparatus shown in the diagram to find out how the temperature of the dilute hydrochloric acid affect the rate of reaction. Your plan should include how your result will show how the temperature of dilute hydrochloric acid affects the rate of reaction. You are provided with dilute hydrochloric acid, calcium carbonate, and common laboratory apparatus. So, to do this particular experiment, we will have to have a certain amount of volume of acid that we're going to use in that particular experiment. All right. So let's say that is like 50 cm cube of dilute hydrochloric acid that we're going to use. Obviously, the same concentration must be used in all the experiment, same concentration and volume. All right. And then we will add to it, for example, like 10 grams of or like 20 grams of calcium carbonate. All right, and we'll like put them together, and at that time we're going to start timing. We're going to repeat the same experiment at higher or lower temperature than the initial experiment that we have done. So let's say if the first experiment is done at 30 degrees Celsius, then the next experiment can be done at 20 degrees Celsius, and then the next experiment can be done at 40 degrees Celsius or 50 degrees Celsius in that way. Then we will represent this information. We'll record the time that is needed for the fizzing to stop. Same experiment, just repeated at different temperatures, and once the fizzing stops, we will consider that particular experiment is finished. So we will then represent that information in a graphical method. All right, what we're going to do for the graphical method, we're going to measure, all right, the mass, all right, at a regular time, for example, like at every minutes. All right, and then we're going to plot a graph. All right, the steepest line, all right, the graph that is going to have the steepest line, all right, is going to be the fastest rate. So once we repeat the experiment in different temperature and we get a steepest line in one of the temperature, then that will indicate fastest rate of reaction. We can also do the same experiment with in accordance with time. All right, so once we will record the time needed for the reaction to end or the fizzing to stop, we can then compare it with different temperatures. All right, the shortest amount of time needed in that particular reaction will indicate highest rate of reaction. Subscribe to the channel, all right, and let the channel grow. Share it with your friends, help them as well. Thank you. See you in the next video. Bye bye.